Hello friends, welcome to this lecture on computer-aided power system analysis. In the last lecture, we have started the discussion of formation of Y bus of an unbalanced power network, and in this lecture also we would be continuing with this topic. So, what we have been discussing is that we have shown a very simple 4 bus network, bus 1, bus 2, bus 3, bus 4, and with this connection, and we also notice that in contrast to the single phase case, in the case of an 3 phase unbalanced system, there would be actually 3n number of injected currents as well as 3n number of voltages. So, then therefore, we should say that there is actually 3n number of injected currents. So, the total number of injected current is 3n and total number of voltages is also 3n. And so, what I will have, so for example, here I will say that it is I1A, similarly here I1B, I1C, and similarly here for example it is I2B, similarly here let us say it is I3C, and similarly for example here I4B, and so on and so forth, so on and so forth. So, now when we are talking about a Y bus matrix, so we actually find out a matrix which would be relating this 3n injected currents with 3n voltages. So, in this case we have to find out the matrix which would be relating this 12 injected currents with this 12 voltages. Now, to do that we need to now essentially model, or rather essentially represent a transmission line. So, now we have to now do something like representation of transmission line. So, representation of transmission line, we are actually talking about 3 phase. Now, suppose now here for this representation of a transmission line we do take some particular notation. Now, suppose I do have a bus M and bus N, this is bus N. Please note that this bus M and N are 3 phase buses. Bus M and N are 3 phase buses, right. So, let us say this is bus M and N, bus M, bus N, bus M, bus N. So, this is phase A, this is phase A, this is phase B, this is phase C, and this is also phase A, this is also phase B, this is also phase C, and in between there is a line, in between there is a 3 phase line. So, this is phase A, phase B, phase C. Now, in the case of a single phase circuit, what we have represented by a single phase circuit, that it has got some series impedance as well as some shunt half line charging susceptance. But in the case of a 3 phase transmission line, what we have, apart from the impedance of individual phase, that is we will essentially an series impedance corresponding to this line at this individual phase, we will also have some other impedance corresponding to this individual phase, we will also have some other impedance corresponding to this this particular individual phase, as well as we will also have their corresponding shunt charging susceptance corresponding to each and every individual phase. But apart from that, we will also have mutual impedances between phase A and B. We will also have mutual impedances between phase B and C, and we will also have mutual impedances between phase C and A. So, then therefore, apart from the self impedances of individual phases, we will also have mutual impedances between any 2 phases. Same thing is also true for the shunt half line charging susceptance. So, then therefore, we need to represent this all these individual impedances as well as this mutual impedances as well as impedances along with the individual phase half line charging susceptance as well as the mutual half line charging susceptance. So, to do that what is done is that we do represent, let us say, bus M like a big bus, I mean big line, and then bus M, bus N. So, this is the bus same N, this is some base same N. Now, in this representation all these phases A, B and C have been actually kind of merged, or let us say subsumed. Now, here of course, we do have I M A of course, and then here also we do have I M B, here also we do have I M C. These are the 3 injected currents. Here also we have I N A, here also we do have I N B, and here also we do have I N C, right. So, these are the 3 injected currents at the individual phases of bus M and N. Similarly, I have these voltages V M A, V M B, V M C. So, these are the phase voltages of bus M, and similarly I do have V N A, V N B, V N C. So, this is the bus M voltages, this is corresponding to bus M, this is corresponding to bus N. Now, for the purpose of representation, or rather for the purpose of concise as well as convenient representation, we do represent these 3 individual currents as a vector saying that it is I M A B C. So, this is a vector. Similarly, we also represent these 3 currents as I N A B C. So, what is I M A B C? So, I M A B C is essentially I M A, I M B, I M C transpose. So, this is essentially 3 cross 1 vector, right. Please note that all these currents are complex quantities. I mean just to avoid unnecessary writing, we are not putting the bars and etc. So, this is a 3 cross 1 current. Similarly, I N A B C is also represented as a vector I N B, I N C. This is also T 3 cross 1. And this now here also we do have voltages V M A, this voltage would be V M B, this voltage is V M C. Similarly, this voltage will have V N A, this voltage will have V N B, and this voltage will have V N C, and these voltages we do denote as V M A B C, and these voltages we also denote as these 3 phase voltages we do denote as mathematically as a 3 cross 1 vector. So, then therefore, V M A B C is actually we write as this in the similar way V M A, V M B, V M C transpose. So, this is also 3 cross 1 vector, and V N A B C is also V N A, V N B, V N C transpose. So, this is also a 3 cross 1 vector. So, then what we have done? We have taken a 3 phase line and we are representing the injected currents and the voltages at these 2 buses in a concise manner. So far these are nothing but the representation of the injected currents and the voltages at the buses, but what about the representation of the lines? So, for the representation of the lines, what we do is we simply write like this. So, what we have got is essentially, so this voltage is VMABC, this voltage is VNABC, current is IMABC, this current is INABC, this is bus N and this is bus M, and the line is being represented by a matrix. It is a 3 cross 3 matrix, and the half line charging susceptances are also represented by a 3 cross 3 matrix. This is also represented by as 3 cross 3 matrix. Now, this matrix we call as Z M N A B C, and we call this matrix as Y M N shunt A B C. Please note that this is in half line, and this also we call Y M N shunt A B C, right. This particular shunt SH is included to note that this is the shunt and this is not the inverse of this. Now, what is ZMNABC? Now, ZMNABC is actually a 3 cross 3 matrix. This is Z, this is a big ZMNABC, this is big Z, and this is a 3 cross 3 matrix. So, this we write as ZMNAA, this is ZMNAB, this is ZMNAC, and similarly this is ZMNBA, ZMNBB, ZMNBC, and lastly ZMNCA, ZMNCB, and ZMNCC. So, now please note that this is a 3 cross 3 matrix, 3 cross 3 matrix, and these quantities are individual impedances. So, these quantities are individual impedances, all these are complex, but we are not including this, we are not putting bar to avoid unnecessary writing. Similarly, YMN shunt ABC also would be denoted as some quantity. So, we would write it as YMN shunt AA, YMN shunt AB, and then YMN shunt AC, then we have YMN shunt BA, YMN shunt BB, YMN shunt BC, and we have similarly YMN shunt CA, YMN shunt CB, and YMN shunt CC. So, this is also a 3 cross 3 matrix. This is also a 3 cross 3 matrix. So, for each and every line, we will have this kind of representation, right. So, now in our case, now in our small example, so now with this particular representation of the lines, now how do I represent so our system, that same small system. So, what we have? We have, so now our small system is something like this, bus 1, bus 2, we are writing it a little broader, bus 3, and we have bus 4, this is bus 1, bus 2, bus 3, bus 4. So, we have this is bus 1, this is bus 2, this is bus 3, this is bus 4. Bus 1 has got current as I1 ABC, and we have already defined what is I1 ABC. Bus 2 has an injected current I2 ABC. Bus 3 also have an injected current I3 ABC. Bus 4 also have an injected current I4 ABC, right. Bus 1 has got a voltage vector V1 ABC, this has got a voltage vector V2 ABC, this has got a voltage vector V3 ABC, and this has got a voltage vector V4 ABC. What about the lines? Lines are so we just note it like this. And then from, and we had our system like this, we had, so from 3 to 4 there is a connection, from 1 to 4 also there is a connection. So, from 3 to 4 where there is one connection, so we write like this. So, this is the shunt, this is the shunt, and from this also we have so essentially. Now, if we look at this, now this is essentially as equivalent. This is essentially an equivalent pi model of the line. This is essentially an equivalent pi model of the line. You may be wondering that from where we will get this matrix. Well, depending upon the configuration of this line, that is what is basically the distance between individual phases and what is the tower height and etc., right. Given all this practical data, right, I mean, then this particular matrices, this matrix as well as this matrix can be easily calculated, but unfortunately that is essentially the out of scope of this course. So, then therefore, we are not calculating this, but as they can be calculated easily depending upon the physical data. So, then we assume that these two matrices are available for each and every line. Now what are this quantity? Now what are these matrices? Now we need to represent. So this is essentially Z12 ABC, and this is Z23 ABC. This would be Z14 ABC, and these definitions we have already given, and this is Z34 ABC. What about these matrices? These matrices would be, this is Y12 shunt ABC, this is Y. Please note that all these are 3 cross 3. So this is 3 cross 3, this is also 3 cross 3, this is also a 3 cross 3. This one is called Y23 shunt ABC. So this matrices, again this is also a 3 cross 3 matrix. Similarly, this is also a 3 cross 3 matrix, and this is Y14 shunt ABC. This is also a 3 cross 3 matrix. We are assuming that each and every line has all these 3 phases. Theoretically, some line can have 2 phase, some line can also have 1 phase, but in that case also this analysis can be carried out, but so far we are essentially neglecting this, because this will actually kind of little more complicate the analysis basic idea. So this is also a 3 cross 3, and this is Y34 shunt ABC. So this is also a 3 cross 3 matrix. So this is the equivalent circuit. So this is the equivalent circuit of the system. Now with this equivalent circuit, so now what we have done, we have simply, so now we have got 4 bus and there are 4 lines, first line, second line, third line and fourth line. And now we are ready to analyze the system. Now what happens? Now as we have done in the case of a balanced system, when we have discussed about the load flow analysis, what we have done? We have simply represented this injected current in terms of the voltages by applying KCL at each and every point. So here also we have to apply KCL at each and every point. So now, so then therefore, this now if I apply KCL at each and every point, so now we can see that I1 ABC is nothing but equal to this current plus this current. I1 ABC is nothing but equal to this current plus this current, and this current is essentially equal to this current plus this current. So then therefore I1 ABC is equal to this current plus this current plus this current, right. Similarly, I2 ABC is essentially equal to this current plus this current plus this current plus this current, because I2 ABC is actually this current plus this current, and this current is this current plus this current, and this current is this plus this. So then I2 ABC is equal to this current plus this current and this and this. Now essentially this current is basically equal to this current plus this current. So then therefore I1 ABC is equal to this plus this plus this plus this. What about I3 ABC? I3 is ABC is equal to this current plus this current, and this is equal to this plus this, and this current is equal to essentially this plus this. And what about I4 ABC? I4 is equal to this current plus this current, and this current is equal to this current plus this current, and this current is equal to this current plus this current. So now I1 ABC is equal to this current plus this current plus this current plus this current, I2 is this plus this plus this, I3 is this plus this, and I4 is this plus this plus this plus this. Please note that this I1 ABC is basically a 3-phase current. So then therefore this current is also 3-phase current, this current is also 3-phase current, this current is also 3-phase current, this is also 3-phase current, right. So all these are essentially 3-phase current. Now if I note now how do I essentially denote this current. Let us say this current is I12 ABC and this current is I12 shunt ABC. This current is I21 ABC and this current is also I21 shunt ABC. This current I can write as I23 ABC. This current I can write as I23 shunt ABC. This current is I32 ABC. This current is I32 shunt ABC. This current is I34 ABC, I34 ABC. This current is I34 shunt ABC. This current is I43 ABC. This current is I43 shunt ABC. This current I can say that this current is I14 ABC, I14 ABC. This current is I14 shunt ABC and this current is I41 ABC and this current is I41 shunt ABC. Now please note that all these currents are essentially 3×1 vector. So we note that all these currents IIJ ABC are all 3×1 vector where I j is equal to 1, 2, 4. So all these currents are essentially 3×1 vector. So then therefore when you would be calculating these currents, right, we really cannot say that this minus this into this, we have to write something else. So now with this we are now ready to analyze the system. Now what would be our next step? So now here one thing we need to understand. Now suppose here now to do this analysis, let us go back a little bit and then try to understand. Now suppose I want to write down the expression of IM ABC in terms of VM ABC and VN ABC. So now what would be that? So I would say that this current is equal to this current plus this current, and I would say that this current is equal to this current plus this current, right. So essentially that is the same thing we have done here. And how this current would be written? This current would be nothing but VM ABC minus VN ABC into inverse of ZMN ABC. So then therefore this current, if I say that IMN ABC, so then IMN ABC can be written as, now what would be the expression of IN ABC? So that is the question. So these issues, that how to write down the expression of IMN ABC and how to write down the expressions of this current and then add them together, these issues would be basically discussing in the next lecture. Thank you.